Okay, ji. So let's start today's lecture. Last time I think मैंने ये इस स्लाइड तक आपसे रिकॉर्डिंग शेयर कर ली है, स्लाइड 21 तक। तो मैं यहीं से स्टार्ट करता हूँ। So we have discussed in the last lecture about the properties of a system, because thermodynamics is all about properties and energy in the form of heat and work. And during any heat or work transfer, properties of the system also changes. So the properties which we know or which we normally use in various thermodynamic system design, those are pressure, volume, temperature, mass, etc. Also, in some special cases, we will be using viscosity, electric resistance, thermal conductivity, and so on. There are many other properties which we shall discuss later on. Okay, then these properties can be divided into two main categories. One is intensive. Intensive properties are those which are independent of mass. So velocity, elevation, pressure, temperature, density, all these are properties, thermodynamic properties, which do not depend on mass of that system. Right, so those are independent of mass. So we have discussed in the previous video lecture in detail about each of those properties, that why those are independent of mass. Then the second major category in which we can divide our properties, the thermodynamic properties of thermodynamic system, is extensive properties. So these are the properties which are dependent on mass. Mass here means the size or extent of the system. So as the mass or size of the system varies, so then the mass, of course, also varies. So these are the thermodynamic properties: volume, momentum, mass, and energy, etc., which are dependent on mass. Then we saw this example. For example, this is a body who has these properties. It has certain mass, certain velocity, certain volume, temperature, pressure, and density. Now, when this body is divided into two parts, then mass will also be divided into two parts. Volume will also be divided into two parts, but temperature, pressure, and density, those are independent of mass, so those will have the same values. Similarly, if we divide this extensive properties like mass or volume with the mass, so whenever we divide extensive properties with mass, like volume per unit mass or momentum per unit mass per unit mass, or energy,
आवाज का इशू आ रहा है।
आवाज का इशू हर क्लास में आता है, इसीलिए मैं आपके साथ रिकॉर्डिंग शेयर करता हूँ, ठीक है। और इसके अलावा मेरे पास कोई इसका क्योर नहीं है। ये लास्ट वीक है, तो इसी तरह गुजारा करना है। नेक्स्ट वीक से फेस टू फेस क्लासेस होंगी, तो इन एनी केस मैं आपके साथ रिकॉर्डिंग शेयर कर रहा हूँ इसी वजह से, ठीक है। ओके जी। So those extensive properties per unit mass, also known as specific properties. So these terms, specific property or specific volume, specific momentum, or specific energy, we shall be using these terminologies quite often in coming chapters. Right. So extensive properties per unit masses are the specific properties. For example, specific volume, specific enthalpy. Enthalpy is a kind of energy which we will discuss in coming chapters. Right. So extensive properties per unit mass means these specific properties, those are also intensive, right? So those become intensive properties. For example, density is intensive, but what is density? Density is mass per unit volume. So mass per unit volume, m divided by v becomes density, but only mass or only volume or extensive properties, but whenever we divide the extensive property with another extensive property, it becomes intensive property. Now it becomes independent of mass. Whether you have 1 kilogram of water or you have 10,000 kilograms of water, the density of both of these waters will be same. So the density of water at about 4 degrees Celsius or at about room temperature, it is about 1000 kilograms per meter cube. So now it is independent of mass. Okay. Next, we will see some more properties we shall discuss here in first chapter. Then there are many other thermodynamic properties which we will discuss in the coming chapters. So here is density and specific gravity. So we know what is intensity, which is mass per unit volume, right? Units are clear. Specific gravity is the ratio of density of a substance, of any substance with respect to density of a water. So this ratio is known as specific gravity. So here you can specific gravity of various materials or substances. So water has 1, blood is 1.05. So the density of blood is a little larger than water, and similarly for other materials. So all those materials whose specific gravity is greater than 1 will not float on the surface of water, those will drown. So ice has lower density than liquid water, so that's why its specific gravity is lower than 1, and we know that ice will always float on the surface of the water. Okay.
एक्सक्यूज मी सर.
जी.
सर हम वाटर के क्यों स्टैंडर्ड लेते हैं यहाँ पे?
Water is a very commonly available material or commonly used material in many thermodynamic systems. आप देखेंगे हम वाटर और एयर को बहुत ज़्यादा एप्लीकेशंस हैं. हम जितनी भी थर्मोडायनेमिक डिवाइसेस अभी स्टडी करेंगे, लाइक स्टीम पावर प्लांट, गैस पावर प्लांट, आपका इवन जो ऑटोमोबाइल इंजन है उसमें भी वाटर यूज हो रहा है इन द रेडिएटर. और जो आपका फ्यूल है, इट्स नॉट प्योर फ्यूल, ये प्योर पेट्रोल या प्योर डीजल नहीं होता. इट इज़ अ फ्यूल प्लस एयर मिक्सचर विच बर्न्स. तो उसमें मेजर पोर्शन जो है, significant portion air का होता है. So air and water are most commonly used working substances in many thermodynamic systems.
Okay, sir. Thank you.
Okay. Similarly, density is mass per unit volume. We can define volume per unit mass, which is called specific volume. So we shall be using this term specific volume quite extensively in the designing of thermodynamic systems. So it is clear if you have a volume, there is some substance whose volume is, for example, 12 meter cubes. It has a mass of 3 kilograms. So we can define density and we can define specific volume. Then there is another term, another thermodynamic property, which is not very common in thermodynamics, but in fluid mechanics, you will be using quite extensively this term, specific weight. So here it is actually weight per unit volume, weight in newtons. When you multiply mass with the gravitation constant mg, it becomes weight, right? So rho into mg. So if there is 1 kilogram of mass, so then you can represent m with 1. So then it becomes simply rho g. So units should be clear. Density, the units of density are kilograms per meter cube multiplied by g, gravitational constant. Its units are meter per second square. Now this term, kilogram meter per second square, this is newtons divided by meter cube. So now this is specific weight. Weight in newtons divided by volume. So that is called specific weight. Newtons per meter cube. If it is kilograms per meter cube, then it is density. Kilograms per meter cube. So If you multiply this kilogram with g, then it becomes newtons. Kilogram meter per second square is newtons, because we know that gravitational constant is different at different places. On Earth, the value is 9.81, but on Moon, it has a different value. So for the same mass, it will have a different weight on the surface of Moon, or on the surface of Mars, or on the surface of Earth. So that's why there is a need to define a term in terms of weight per unit volume, not in terms of mass, because for the same mass, you may have different weight if gravitational constant is different. Okay, so these are the various types of properties which we shall be using. So in this chapter, we just want to have a clear idea what is meant by thermodynamic property, and what is meant by heat, what is meant by work. So heat, work, and properties of the system, that is what all thermodynamics about. Okay. Now there is a concept of continuum. You would have learned in fluid mechanics also. So here we shall repeat the meaning of continuum. As we know that substances are, every substance is made up of atoms, small atoms, right? In case of solids and liquids, these atoms are very near to each other. But in case of gases, the distance between these molecules and atoms are quite large. So there are actually empty spaces between molecules if it is gas, right? So there will be empty spaces. In case of liquids, the empty spaces are very small. In case of solids, the empty spaces are even more smaller, right? But in when we say continuum, this term is derived from continuous. So there is another term which is called non-continuum, means non-continuous. So the concept of this continuum is quite similar to what we have learned in macroscopic versus microscopic point of view. So when we say continuum, it means we are not concerned with the behavior of these individual molecules. We can treat this whole substance as being continuous by disregarding the action of individual molecules. We are treating that substance as a continuous substance without any holes in it. Right. So this continuum concept is, of course, is only an assumption, a convenient assumption that will lose its validity when the mean free path between molecules. So this substance is continuum, but if I draw another substance, the same substance, but with very less number of molecules. For example, here you have another substance, but very few molecules. This one. Now the average distance between these molecules is of the size of this substance. Here in this case, the average distance between molecules is very small compared to the overall size of that substance. So here, in this case, we can treat it as continuum substance, but this one cannot be treated or assumed as continuum in this case, because the distance between molecules is of the order of the size of that object, right? So for example, in case of जी किसी का कोई क्वेश्चन है?
सर एक क्वेश्चन है कि ये जो डिस्टेंस है सर वो कितने को हो तो हम इसे कॉन्टिन्यूम और डिसकॉन्टिन्यूम कह सकते हैं। फॉर एग्जांपल जिस तरह हम पढ़ते हैं कि गैसेस में एक मॉलिक्यूल दूसरे मॉलिक्यूल से तकरीबन 300 टाइम एक दूसरे से वो दूर होता है।
मैं
तो
आपको
कितने
अभी एक्सप्लेन कर रहा हूँ, ये आ रहा है आपका आंसर। ओके, सो अभी तक हमने क्या कहा कि व्हेनेवर द मीन, ये जो मीन फ्री पाथ है ऑफ मॉलिक्यूल्स, द डिस्टेंस बिटवीन मॉलिक्यूल्स, if it is smaller, if this, for example, this is the average distance between these molecules, if this distance is smaller than the total size of the object, it's significantly smaller than the overall size of the, ये अपना माइक ऑफ कर लें, या अगर कोई क्वेश्चन है तो पूछ लें। ओके, So then it can be treated as continuum. But when the distance between molecules is significantly large, for example, in case of vacuum technology, when we create vacuum in a space, for example, this was air with no vacuum, or air was present here at 1 atmospheric pressure. But here the same air is present, but at a very low pressure, right? So, for example, this pressure is 0.00001 bar, right? In this second case, here the pressure was 1 bar. So here we have created vacuum. So now this cannot be treated as continuum, or we cannot apply the laws of continuum mechanics on this substance. We can apply the laws of continuum mechanics on this substance, right? So that is the concept of continuum. So continuum mechanics is a branch of mechanics which deals with the mechanical behavior of materials, which can be modeled as continuous mass rather than as discrete particles. Here those are discrete particles because the gaps between molecules are significantly larger. So modeling an object, when you model an object as a continuum, it assumes that the substances of the object completely fills the space which it occupies. So modeling objects in this way ignores the fact that the matter is made up of small atoms. And when it is made up of small atoms, if we are at the molecular level, then we have to account for the empty spaces between the molecules, right? So the fundamental physical laws, such as conservation of mass, which you will study in thermodynamics, also in fluid mechanics, all those laws of conservation of mass, conservation of momentum, and also conservation of energy may be applied to such models, this one, which, and we can derive differential equations which will describe the behavior of such objects, and some information about the particular material studied is added through constitutive relations for this continuum. Okay, whatever I have described now, it is written in the book and also on this slide. So let me go through those points. So whatever we have discussed is written here, right? So which you can read by yourself. Now, in this course or in majority of thermodynamic devices, which we shall be studying as mechanical engineer, we shall limit our consideration to substances that can be modeled as continuum. So we shall not be dealing with extraordinary vacuum in our course or in our majority of thermodynamic applications, for example, steam power plant, automobile engines, refrigeration and air conditioning. In all these systems, our substances, our systems will be modeled as continuum, not as non-continuum. अब इसकी एक एग्जांपल जो अभी एक स्टूडेंट ने क्वेश्चन भी पूछा, फॉर एग्जांपल here you see a diameter of oxygen molecule is this one molecule of oxygen has 3 into 10 to the power minus 10 meters. So this is a very small diameter. And the one molecule of oxygen, its mass is 5.3 into 10 to the power minus 26 kilograms. So it is very, very, very light. So it is so small and it is so light that we cannot even see with our eye. Okay. And the mean free path between oxygen molecules at 1 atmospheric pressure. 1 atmospheric pressure means it's not a vacuum. So it is at normal ambient pressure. The mean free path of oxygen molecules is about 6.3 into 10 to the power minus 8 meters. So this is also very small, this mean free path between two molecules, but it looks bigger because molecule itself is so small and its mass is so small. So this distance is also very small. Now, for example, there are now under these conditions at 1 atmospheric pressure and 20 degrees Celsius, when oxygen has this much diameter, oxygen molecules has this much diameter and mass is this much, then there will be how many number of molecules in one tiny volume. Which volume? 1 millimeter cube. So can you imagine 1 millimeter cube? It's a very small cube. So if you know what is millimeter, then you can imagine a cube of 1 millimeter. So in just a very small 1 millimeter cube of volume will have this much molecules of oxygen in gas, oxygen in gaseous form. 3 into 10 to the power 16 molecules will be present. So these are huge number of molecules, but molecule itself is very small. Its mass is so small, so that's why there are huge number of molecules in just 1 millimeter cube. Right. So under these conditions, we can definitely say that that is continuum. We cannot assume non-continuum because at 1 atmospheric pressure in this small cube of 1 millimeter cube has this number of molecules, 3 into 10 to the power 16. So that's why we can definitely assume continuum. And this is we are talking about gas. So for now you can imagine for liquids and solids, the number of molecules which will be present in 1 millimeter cube would be much larger than this one because we are talking about gas. So definitely. So here it is also shown in terms of a figure also. So also at molecular level in gases they are freely moving, but molecule itself is so small that there are about 3 into 10 to the power 16 number of molecules in just 1 millimeter cube of volume. So that's why we can model this gas as continuum. So that is the concept of continuum, and we shall be using continuum mechanics laws and principles to model and to design our thermodynamic system. So in case if you are dealing with ultra vacuums where this the average distance between molecules is of the order of the size of the substance. So in that case, we have to go for non-continuum. So all of you are with me, or you're listening?
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
Okay.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
सर आवाज
Okay.
कट कट
इधर
के
ही
आ
है
रही
सर.
है
आवाज कट के आ
कट
रही है।
यस सर
इसलिए मैं बाद में रिकॉर्डिंग शेयर करता हूँ, ठीक है?
थैंक यू सर
ओके।
एक्सक्यूज मी सर।
जी
सर जो हमें टाइम टेबल दिया गया है उसमें तो आज क्लास नहीं थी थर्मोडायनामिक्स की।
हाँ, उसमें कल क्लास थी ना 2 आवर्स की, सेक्शन बी की, वो नहीं हुई। और वो इसीलिए नहीं हुई कि ये जो इश्यूज आते हैं तो बार बार एक लेक्चर रिपीट करना पड़ता है, तो इससे बेहतर है कि दोनों सेक्शन से इकट्ठे एक ही दफ़ा क्लास ले लें। और इन एनी केस आप में से मेजॉरिटी ऑफ द स्टूडेंट्स आर वेटिंग फॉर रिकॉर्डेड लेक्चर, ठीक है? क्योंकि इसमें
ठीक है
कोई
सर।
इश्यूज आते हैं, तो
सर
इसलिए
ये फिर 2 आवर्स वाली होगी।
लेट्स सी ये भी कितना चलती है, ठीक है? 11 तक का टाइम है हमारे पास। 11 ओ क्लॉक पे आपकी फ्लूइड मैकेनिक्स की क्लास है। सो देखते हैं कि हम कब तक चलते हैं। सो ये क्लास एक आज होगी आपकी ऑनलाइन और एक आपकी थर्सडे को होगी अकॉर्डिंग टू टाइम टेबल।
ठीक है सर।
बाकी जो क्लासेस हैं वो नहीं होगी सिर्फ इस वीक में। हम इन्हीं ये जो ऑनलाइन क्लासेस हैं आज की और थर्सडे की, इसमें हम इस पूरे वीक का कोर्स कवर कर लेंगे, ठीक है?
ठीक है सर।
फिर नेक्स्ट वीक जो एवरीथिंग विल बी नॉर्मल। ओके, माइक क्लोज कर दें, माइक ऑफ कर दें।
सर लेक्चर पूरा होने पर काइंडली सर ऐसे जल्दी अपलोड कर दीजिएगा।
लेक्चर अपलोड किया हुआ है
सर
कंप्लीट।
आपकी आवाज कट रही है।
ठीक है सर।
चैप्टर 1 कंप्लीट बहुत दिनों पहले से अपलोड किया हुआ है इसके नोट्स, ठीक है? जो
ठीक है शुक्रिया।
रिकॉर्डेड लेक्चर्स हैं वो आपको उसी दिन मिल जाते हैं, ठीक है? ओके जी। Next is state and equilibrium. The next concept is state. So here we are discussing fundamental concepts. So various concepts which will be utilized in advanced topics to design thermodynamic systems. So यहाँ पे सिर्फ वो fundamental concept use हो रहे हैं because next chapter में onwards we will be using these terminologies. So next is state. So इसको भी मैं आपको explain करता हूँ with the help of that example. Let's take the example of a boiler in which water is entering and water is leaving. For example, water is entering at 20 degrees Celsius, 10 bar. So what are these? These are properties of the system. Temperature, pressure, this water will have certain mass, will have certain volume. So all these are thermodynamic properties. So with the help of these thermodynamic properties, I have one state. I have defined a state. This is state one, right? So condition of the system at any instant of time. ये जो ऊपर definition लिखी हुई है, as described or measured by its properties. So we are describing a state of any thermodynamic system with the help of these thermodynamic properties. At this state 1, it has temperature of 20, it has pressure of 1 bar. Now heat is added, so this state 1 will change to another new state. This is another new state. What will be this state? At this state, now we can define another state by a different set of thermodynamic properties. Now it will have temperature of 300 degrees Celsius, pressure is still 1 bar, and it will have certain new volume because now this liquid water is converted into gaseous water, so its volume would have increased. So इसी point के ऊपर इसका कोई volume भी होगा. इस point के ऊपर now it will have a different density, a different thermal conductivity, and all other thermodynamic properties. So now what was this point one? This was a state. Point two, another state. So now it enters into a turbine and work is extracted. So now it will change to a new state. So this was state 2. Now it will have a new state 3. A new temperature. Temperature is will again drop. Pressure will drop. So what are these? Point 1, 2, and 3. Point 1, point 2, point 3. All these are states. Condition of a system. So let's read again. Condition of the system at any instant of time. Condition of a system at any instant of time, right? State 1, as described or measured by its properties. जी किसी का माइक ऑन है, प्लीज ऑफ करें इसे.
जी सर. सर एक क्वेश्चन है,
जी
इसे जी सर इस तरह हम कह सकते हैं कि स्पेसिफिक कुछ पोर्शन के बाद जो उसमें मैकेनिकल प्रॉपर्टी चेंज आती हैं उनको हम स्टेट कह सकते हैं.
मैं आपको बताऊं, देखिए ये जब स्टेट थी, इस स्टेट के ऊपर ये जो स्टेट 1 थी, एवरीथिंग वाज इन बैलेंस कंडीशन. ठीक है. सो व्हेन एवरीथिंग इज इन बैलेंस कंडीशन, उस वक्त उसका क्या टेम्परेचर है, क्या प्रेशर है, एटसेट्रा. इस वक्त हम मैकेनिकल प्रॉपर्टीज की, हम थर्मल प्रॉपर्टीज में ज्यादा interested हैं because we are discussing thermodynamics. In case of mom, you will be interested about mechanical properties. Case point के ऊपर इसकी ductility कितनी है, brittleness कितनी है, etc. etc. But here we are discussing thermodynamics. So at this point, at this state, it has these properties. So this state is defined by these thermodynamic properties. At this state, now between 1 and 2, this is not a state. This is change of state from 1 to 2. Because there is a process of boiling occurring. So now you are shifting from one equilibrium state to another equilibrium, new equilibrium state. Then another new equilibrium state to point 3. So these are state, right?
सर मतलब कि जब तक वो प्रॉपर स्टेबल इक्विलिब्रियम में नहीं आ जाता तब तक वो स्टेट चेंज नहीं कहेंगे हम उसको.
नहीं, जब वो किसी इक्विलिब्रियम कंडीशन में आ जाता है, then we say it is a state, it is a new state.
ठीक है. Okay, sir. Thank you.
So, in other words, each unique condition of a system, each unique, here this unique condition was at point 1. What was this unique condition? Defined by 20 degrees Celsius and 10 bars. Another unique condition is this one, 300 degrees Celsius and 10 bar. Another unique condition, and so on, the after condenser and after pump. right? So all these are point 1, point 2, point 3, and so on are states. So at a given state, all properties at a given state at point 1 or at point 2, all properties, all thermodynamic properties of a system have fixed values. इस point के ऊपर इसकी कोई fixed values हैं, इस point 2 के ऊपर फिर कोई नई fixed values and so on. Right. So any operation in which one or more properties of a system change is called change of state. ठीक है, any operation, यहाँ कौन सा operation हुआ है जिसकी वजह से इसकी state change हुई है? That was the operation of heating or boiling. There is another operation that is called turbine work or expansion of fluid in the turbine. ये जो यहाँ पे जो change आई है, change of state from point 2 to point 3. This is change of state. ठीक, question? अगर क्वेश्चन नहीं है तो अपना माइक ऑफ कर दो. Okay, जी. So here you see another example which you will normally see in your book or notes. तो ये वही cylinder piston mechanism, that is its initial state, initial some temperature, volume. Now it changes to a new temperature, new volume, and during this process temperature remained constant, volume is changed. So this is state 2, new stable state. This was initial state 1. So during this process some process has during this change in state some process has occurred. Maybe it was heated up, or maybe the weight was removed from this piston, so that's why this gas has expanded from state 1 to state 2. Both of these states are equilibrium states. So thermodynamics is dealing with equilibrium states. So ये जो हमने example देखी इसमें this is one equilibrium state. Equilibrium is clear when something is not changing, everything, a state of balance is called equilibrium. ठीक है? So it means there are no unbalanced forces acting on your substance. That's why everything is fixed, it's not changing. So thermodynamics is always dealing with equilibrium states. This is an equilibrium state, another equilibrium state, another equilibrium state. Now, so equilibrium is clear. Now we can define different types of equilibriums. For example, if temperature is same throughout the system, then it is called thermal equilibrium, right? At this point, temperature was constant, so it was in thermal equilibrium. At this point, a new temperature, but now it is fixed. Between these 2 points, it was not in thermal equilibrium. But from this point, at the inlet of boiler till the exit of boiler, that was not in thermal equilibrium. But at this point 1 and at this point 2, it is in thermal equilibrium. But between 1 and 2, it was not in thermal equilibrium. So ये जो book में example दी हुई है, that is should be clear. For example, that is some substance who has different temperatures at different places, right? And after some time, the whole substance has the same, or the whole system has the same temperature. So that is in thermal equilibrium. Here it was not in thermal equilibrium because temperatures were different and your substance was changing temperature. Then there is mechanical equilibrium. Mechanical equilibrium means if there is no change in pressure at any point of the system with respect to time, then it is called mechanical equilibrium. For example, ये जो process था boiling का, during this process of boiling, temperature was changing, but pressure was constant. So you may say between 1 and 2, it was in mechanical equilibrium because pressure was not changing. But here it was not in mechanical equilibrium. In case of turbine, pressure was also changing during this process. So that was not in mechanical equilibrium. So in this process of boiling, it was in mechanical equilibrium during this process, but not in thermal equilibrium. But at this state, everything is in equilibrium, or at this new state, everything is in equilibrium. Then there is another term which is called phase equilibrium. For example, in some pot, let me show it. For example, here you have container in which some liquid water is present, and this space has some gaseous water, some of the water which evaporates from its surface, and here you have vapors in this portion, in the upper half. In the lower half, you have liquid water. In the upper half, you have gaseous water. Okay. Now, with respect to time, if the amount of liquid water and the amount of gaseous water is not changing, it means the number of molecules which are evaporating is equal to the number of molecules which are condensing. So what will happen, that the level of this liquid water and the level of this gaseous water is not changing with respect to time. Then it is called then you may say it is in phase equilibrium, because phase is not changing. The amount of liquid and the amount of gaseous water present in this container is constant with respect to time. ठीक है. So then it is in phase equilibrium. Phase means liquid phase, gaseous phase, or solid phase. ठीक है. So if a system involves two phases, yes, मैंने आपको example दी. Here you have two phases, and when the mass of each phase reaches an equilibrium level and stays there. So now it is a state where the liquid and gaseous portion are not changing their amount. So then it is in phase equilibrium. Then another is the chemical equilibrium. Chemical equilibrium means that G का question है.
जी सर। सर ये फेज इक्विलिब्रियम हम बॉयलर और जो टरबाइन है इसके अंदर नहीं यूज़ कर सकते ना, कि बॉयलर के अंदर वाटर आ रहा है और स्टीम निकल रही है, फेज चेंज हो गया, लेकिन टरबाइन के अंदर स्टीम जा रही है और स्टीम ही निकल रही है, सिर्फ वो प्रेशर और टेम्परेचर चेंज है, तो लेकिन फेज
Exactly.
तो सेम ही है ना।
हाँ, वहाँ आप कह सकते हैं कि it is in phase equilibrium in case of turbine. तो जब हम अभी डिटेल में स्टडी करेंगे थर्मल पावर प्लांट, तो you will see that at the exit of turbine, some of the gas, some of the steam converts to liquid water. Why? We shall see later on.
ओके सर।
Then there is another type of equilibrium which is called chemical equilibrium. If chemical composition of a system does not change with time, that is, no chemical reaction occurs, then it is in chemical equilibrium. For example, here in case of boiler, uh, how we are getting this heat by burning some fuel. So because fuel is burning, that's why its chemical phase is changing. Fuel यहाँ पे burn हो रहा है, this fuel which is burning. So during burning process, its chemical nature is changing, and that's why this chemical energy is converting into heat. So this is not in chemical equilibrium. But what about this water? ये जो water in हो रहा है in the boiler, it was in liquid state and now it is converted into gaseous state. So during this process on the water side, chemical nature is not changing because it is still water. It was here liquid, only phase was changing. So this was not in phase equilibrium, but this water is in chemical equilibrium because the chemical nature of water is not changing. It is only the phase which is changing. So on the water side, it is only the phase which is changing, but not the chemical nature. So you may say on the water side, it is in chemical equilibrium, but on the fuel side, it is not in chemical equilibrium because it is changing its chemical nature. When fuel is burnt, it changes its chemical nature. It converts into a number of gases at a very high temperature, and heat is transferred from this high temperature gases. So this fuel is not in chemical equilibrium, but this water on the other side, you may say it is in chemical equilibrium. So these are the various types of equilibriums which we will be dealing in thermodynamics. Okay. Next is the concept of state postulate. Now, what is meant by state postulate? Here you see in figure some nitrogen gas is present inside this container. And what is this container? It's just a piston cylinder mechanism, most probably, right? So here you see the temperature and volume are shown. The specific volume, meter cubes per kilogram, and temperature. Temperature is an intensive property. Specific volume is also an intensive property. Intensive property means which are independent of mass. So now, once you know at least two independent intensive properties, then you can fix its state. If only temperature would have been given, अगर अब सिर्फ temperature known होता, then you cannot find out its exact state कि इस temperature के ऊपर at 25 degrees Celsius, what is its pressure, what is its pressure, or what is its volume. But if you know at least two independent intensive properties, for example, यहाँ पे temperature भी known है, specific volume भी known है. When two intensive properties are known, then all other properties will have certain values automatically. यानी जब टेम्परेचर और वॉल्यूम नोन है तो इस टेम्परेचर और वॉल्यूम के ऊपर इस नाइट्रोजन का कोई ना कोई प्रेशर भी होगा. इस टेम्परेचर और वॉल्यूम के अगेंस्ट दिस नाइट्रोजन विल हैव सर्टेन डेंसिटी. इस टेम्परेचर और वॉल्यूम के अगेंस्ट दिस नाइट्रोजन विल हैव अदर थर्मोडायनेमिक प्रॉपर्टीज. इसकी कोई एक स्पेसिफिक विस्कोसिटी है. सो वी नीड टू फिक्स अ स्टेट बाय नोइंग एट लीस्ट टू independent thermodynamic intensive properties. So at least two should be known to fix a state. So that is called state postulate. मैं इसको अब रीड करता हूँ जो यहाँ पे राइटिंग की हुई है. We do not need to specify all properties in order to fix a state. हमें सब की सब properties यहाँ define नहीं करनी to fix a state of any substance. At least any two. Once a sufficient number of properties are specified, the rest of the properties assume certain values automatically. Once a sufficient number of properties are specified, for example, temperature and volume are known, then the rest of the properties, for example, pressure, density, specific heat, all other properties will have certain values automatically. So the number of properties required to fix the state of a system is given by state postulate. So that is called state postulate. So इसको अब यहाँ पे definition की form में लिखा हुआ है, the state of a simple compressible system. Now what is meant by simple compressible system? This system is simple compressible if we neglect gravitational effects, right? Simple compressible system means there are no gravitational effects, there are no surface tension effects, there are no electrical and magnetic effects. If we are neglecting electrical, magnetic, gravitational, or surface tension effects, then it is known as simple compressible system. For example, you want to know what is the potential energy of this nitrogen. So potential energy of this nitrogen cannot be calculated only on the basis of temperature and volume. Now you would need a third property. And what will be that property? To know the potential energy of this gas, H, height of this nitrogen with respect to some datum. So in case, but when you do not need potential energy, you just want to know what is pressure or density, then these two are enough. But if you want to know what is the electrical charge in it, then you may need to know what is the electrical resistance, etc. Electrical properties are known, should be known, right? So if in thermodynamics, we are not concerned with electrical magnetic properties. So that's why we do not need to specify some extra property to fix a state. So, but in some cases, we are interested to know the potential energy of a substance. So then we have to define a third property, which is H. But if those effects are not there, then it is called a simple compressible system. So the state of a simple compressible system is completely specified by two independent intensive properties. Now, what is meant by independent intensive properties? We know these are intensive properties, but these should be independent also. So ये थोड़ा सा tricky concept है, मैं इसको आपको explain करता हूँ in a different way. For example, उसी boiler की example लेते हैं. In case of boiler, steam is entering, so liquid water is entering, liquid water is leaving. इसको अब मैं शो करता हूँ इस प्रोसेस को on temperature versus volume diagram. Temperature versus volume diagram. It had initial temperature of 20 degrees Celsius, an initial volume of, for example, 1 meter cubes per kilogram, small v specific volume. So now you can fix it here, 20 degrees Celsius, 1 meter cube. So this is the initial state 1. Now if you heat this water, its temperature will rise and also its volume will rise. You are heating a substance, so its temperature is rising, but at the same time its volume is also rising. And in case of boiler, or in case of this process which is shown here, pressure is fixed. That's why this water will start to boil. If pressure is 1 bar, then it will boil at 100 degrees Celsius. So it means this whole line is representing 1 bar line, right? इस पॉइंट के ऊपर जिस तरह हमने पहले स्टीम पावर प्लांट को जब हम डिस्क्राइब कर रहे थे, हमने वहाँ से डिटेल में स्टडी किया था. नाउ इट विल स्टार्ट टू बॉयल. ठीक है, नाउ टेम्परेचर will remain constant, but volume is still increasing because we are heating water. It is still expanding. Liquid water is converting into gas until all of the liquid water is converted into gas. Now if you further supply heat, its temperature will start to rise again. Now इस पूरी line के ऊपर, starting from here, from 1 till this point 2, on this whole line, one property was constant, and that was pressure. That's why you have kept pressure constant, and that's why it boiled at 100 degrees Celsius. अब इसी प्रोसेस को अगर आप रिपीट करें पॉइंट 1 से, लेकिन प्रेशर को इंक्रीज कर दें, प्रेशर इज नॉट 1 बार, फॉर एग्जांपल प्रेशर इज 10 बार, तो यही जो fluid है, it will have such line because now it will boil at a higher temperature. This higher temperature के ऊपर now there will be a phase change from liquid to gas, and then it will be in gaseous phase. So by changing the pressure, what has done, this boiling point is increased. Similarly, if you drop the pressure starting from the same 20 degrees Celsius, it will boil at some lower temperature. So a similar line will be there, but now at a lower pressure. For example, this is 0.2 bars. This was 10 bar. Now what I want to explain is this thing. Now you can see that at 20 degrees Celsius temperature, this is 20 degrees Celsius temperature line on this temperature versus volume axis. You may have different volumes. ये वॉल्यूम भी हो सकता है, ये वॉल्यूम भी हो सकता है, आपके वाटर का ये वॉल्यूम भी हो सकता है. ऑल दीज आर डिफरेंट पॉसिबिलिटीज, बिकॉज ये वॉल्यूम किस तरह चेंज हो रहा है, प्रेशर से. तो जब 20 डिग्री सेल्सियस पे जब 1 बार प्रेशर था, दिस वाज वॉल्यूम. व्हेन प्रेशर वाज इंक्रीज्ड, उसी वाटर का 20 डिग्री सेल्सियस हैड लेस वॉल्यूम. व्हेन प्रेशर वाज ड्रॉप्ड, then the same fluid will have this volume. So it means at 20 degrees Celsius, there is not one fixed volume. Volume could be different depending upon pressure. So when we say, अब मैं explain क्या करना चाह रहा हूँ, आपको explain ये करना चाह रहा हूँ. ये जो यहाँ लिखा हुआ है ना, when we want to fix a state of a substance, we need two independent intensive properties. So अगर आप सिर्फ टेम्परेचर डिफाइन करते तो इस पूरी लाइन के ऊपर वॉल्यूम ये भी हो सकता था, ये भी हो सकता था, ये भी हो सकता था. But now you have defined 20 degrees Celsius and a fixed volume. Now it fixes its state clearly. So that's why you need at least two independent intensive properties to fix a state. Independent temperature and volume. जब ये दोनों आपने define किए, now its state is fixed. अगर आप सिर्फ 20 degree Celsius, if you just say only 20 degree Celsius or only volume, अगर आपने सिर्फ volume बताओ, तो इस volume पे there could have been different possibilities of temperatures. Right. So to fix a state completely, we have to define two independent intensive properties. Okay, so that is called state postulate. Even if this is not clear, we shall be repeating these concepts in chapter 3. ठीक है, अगर अभी आपको ये क्लियर, because chapter 3 में हमने इस पूरे phenomena को in detail study करना है. So this will be clarified there also. So simple compressible system मैंने आपको explain कर दिया. If a system involves no electrical, magnetic, gravitational, motion and surface tension effects. Motion means कि for example I'm interested to know what is its kinetic energy. तो kinetic energy के लिए तो only temperature and volume are not enough. We need to know what is its velocity. Only then I can tell what is its kinetic energy. ठीक है. इसी तरह अगर आपको gravitational effect find करना है, so then I need to define its height, right? So simple compressible system का मतलब ये है कि उसमें कोई electrical, magnetic, gravitational, motion और surface tension effects नहीं है. Then it is a simple compressible system. And to fix a state of a simple compressible system, only two independent intensive properties. और independent का क्या मतलब है ये मैंने आपको explain कर दिया. Gravitational effect. Two properties are independent. ये जो मैंने इस ग्राफ में आपको एक्सप्लेन करने की कोशिश की है, it means कि two properties are independent if one property can be varied while the other one is held constant. यहाँ आप देखें टेम्परेचर को आपने कांस्टेंट रखो तो you may have different possibilities of volume, right? So by fixing one temperature you can change, you may have different possibilities of volumes. Then this temperature and volume are independent properties. These are independent properties and we need to define two independent intensive properties to fix a state. Okay, so temperature ये मैंने आपको explain कर दिया. Temperature and specific volume for example are always independent properties and together they can fix a state of a simple compressible system. And what is simple compressible system? Which does not involve any electrical, magnetic, gravitational motion and surface tension effects. Okay, ये कुछ काफी tricky सा concept है, but this will be clarified in coming chapters. क्योंकि ये जितने भी concept हम chapter 1 में पढ़ रहे हैं, those will be repeated in practical examples. So ये सब clarify हो जाएंगे. In exams मैंने आपको पहले बता दिया, I will never ask, we shall never ask you write a note on state postulate or what is meant by simple compressible system. इस तरह का question हमने देना ही नहीं है जिसमें आपने in definitions को memorize करना है. We shall be asking these theoretical questions in terms of MCQs. ठीक है, सिर्फ आपको yes no बताना है या 4 options दिए होंगे उनमें से आपने कुछ select करना. So you just need to have a clear concept of these definitions. So you do not need to memorize any of these things. Okay, just need to have a concept. Okay, let's move on. Another concept which we'll be using in thermodynamics, that is processes and cycles. Right. So what is a process? यहाँ पे आप एक process देख रहे हैं जिसको हमने show किया on pressure versus volume diagram. Piston is compressing a gas. Right. So initial volume was V1, higher volume V1. Initial pressure was some low pressure P1. Now it is compressed till this point. So this was initial state, initial equilibrium state, and this is final equilibrium state. Between these two states, there is some process occurring. Okay. So this is a process which is joining the two states, or the change of state is known as process. And every process will be following certain path. For example, यहाँ show किया हुआ between 1 to 2, it is following this path. Maybe in some other cases, it may be following some different path. For example, between 1 to 2, it may be following such path. It may be following such path, linear path, or it may be following such path. So there could be different paths which your process can follow between 1 and 2, right? But the state 1 is fixed, state 2 is fixed, but process may follow different paths depending upon the nature of your system or the nature of your process. So क्यों different paths होते हैं, we will discuss in coming chapters, but here we just need to know what is meant by process or process path and what is meant by state. This is state, this is another state. Between two states, there is a process which can follow any path, any specific path, right? So ये जो मैंने यहाँ एक्सप्लेन कर दिया, any change that a system undergoes from one equilibrium state to another is called a process. ठीक है, और इसको मैं एक्सप्लेन अगर कर दूँ with the help of our example, same boiler, turbine. ठीक है, तो यहाँ क्या हो रहा है, steam is entering, steam is leaving, so this was its initial state, this was its final state. Between these two states there is a process. ठीक है, this was state 1, this is state 2. Similarly here you will have state 3. So between any two states there is a process which is following certain path, which you can show on any thermodynamic diagram. This is called, ये जो आप diagram देख रहे हैं, that is called thermodynamic property diagram, because दोनों x और y axis पे कोई ना कोई thermodynamic properties are shown. Pressure versus volume. You may have volume versus temperature. So there will be many different thermodynamic property diagrams which we will discuss in coming chapters. But first of all, we should have a very clear idea about state, about process path, about thermodynamic property, etc. So process is clear, path is clear, right? So to describe a process completely, ये जो इस process को completely describe करने के लिए what we need to specify: initial state, final state, and also the path, which path it is following. And during this process, what is happening? It is interacting with the surroundings. Why this process has taken place? Because surrounding से कोई work done हुआ था, surrounding से कोई energy transfer हुई इस system में, and that's why system state is changed. Or इस case में this was your system, and this portion of the system, is defined by its boundary, and this portion of the boundary was movable. Initially this boundary was here, now this boundary is shifted to here because this boundary is movable. Or why this process has taken place? Because from the surroundings some work is transferred to this system. Similarly here, this was initial state, this is final state. Why there is a change of state? Because there was a process, और वो process क्या था? Boiling का process. And during this boiling process, some energy, heat energy, is transferred from the surroundings to the system. So hopefully all these terminologies are clear. Now we can also define processes into two ways. Just go. Erase. Okay, so the next is quasi-static or quasi-equilibrium process. इसका क्या मतलब? So here, when a process proceeds in such a manner that the system remains infinitesimally close to an equilibrium state. Now, what is meant by this thing? ये जो process हो रहा था from 1 to 2, इस process को हमने show किया हुआ this path से. So how we can know about this path? Only if we assume that this process was passing through a number of equilibrium states. That's why we have been able to know its path. ये path हमें क्यों पता लगा? Because your system or your process was passing through a number of equilibrium states which we can join to know the path. For example, if this is not an equilibrium process, then we may not know that this point 1 to 2 इसने कौन सा path follow किया. If we do not know which path your process is taking to change its state from 1 to 2, it means we cannot trace its path. Why we cannot trace its path? Because it is not passing through a number of equilibrium states which we can trace. Then it is called non-quasi equilibrium process or non-quasi-static process. So whenever we say quasi-static or quasi-equilibrium process, it simply means when a process, this process, for example, this one, proceeds in such a manner that the system remains infinitesimally close to an equilibrium state. So we are assuming that this system is passing through a number of equilibrium states which we can trace, and that's why we know its path. For example, this system is following this path. So what is the work done? Because during this process you have transferred some work, so we can find out its work. The area under this curve, what is this area under this curve? That is the work done, because this area under this curve represents PV, because on y-axis we have pressure which is changing, on x-axis this is volume which is changing. So ये जो change है in PV product, and PV product is work done. ये units आप देखते हैं न्यूटन पर मीटर स्क्वायर मल्टीप्लाइड बाय मीटर क्यूब, यही होते हैं न्यूटन per meter square, because during this process pressure was changing and volume was changing. Pressure is Newton per meter square multiplied by volume is meter cube. So what is left? Newton meters. What is Newton meter? Joules or energy. Yes. So it means the PV product. And what is PV product? This area under this curve represents, because this side is pressure and this side is volume. So if we know the equation of this line, we can find out its area under work. ये हम करेंगे in chapter 3-4. So it means if we know the path, only then we can find its area under this path. And if we know the area, then we can find out what is the work done. So I want to know, to change its pressure from point 1 to point 2, how much work should be given, how much energy should be given to this gas. So how I can calculate? If I can draw its path. If I can draw its path, then I can find out its area under this path. When I know this area, then I can find out its work done, because area under this curve represents this PV product, and PV product represents energy. So as an example, I have told you. So that's why quasi-static is necessary for us, so that we can trace the path. We should know the path, and then we can find out its area under this curve. So that is called quasi-static. इसकी एक example यहाँ show की हुई है. Here you see piston is getting compressed, but this process is very slow compression. ठीक है. So we are doing work onto this piston, but during this energy transfer, this process is very slow. This piston is compressing this gas, but very slowly. So when it is very slowly, so what will happen? When piston is moved slowly, what will happen? Molecules here, molecules of a certain gas will have enough time to redistribute, and there will not be a molecular pileup. स्लो कंप्रेशन है, ये मॉलिक्यूल्स यहाँ पे पाइल अप नहीं होंगे. जो जितनी भी एनर्जी यहाँ ट्रांसफर हो रही है वो इवनली और यूनिफॉर्मली विल बी ट्रांसफर्ड इन द होल गैस, राइट. सो प्रेशर विल राइज एट द सेम रेट in all locations, and this slow compression can easily be shown with the help of, because now we will know when it is changing its state. Let me show it. This was state 1, and this, for example, this is state 2. Now between 1 and 2, it is passing through a number of equilibrium states, because we can measure its pressure and volume during all these states, because when it is moving very slowly, this pressure distribution is evenly distributed in the whole gas, and we can calculate or we can measure its new pressure at this point, new volume at this point, because this pressure and volume distribution is very even or uniform, which we can measure. Another equilibrium condition, another equilibrium, all these are equilibrium states which we can show on a diagram, and that's why we can trace its path. So slow compression is an example of a quasi equilibrium process. Why it is quasi equilibrium मैंने यहाँ explain कर दिया. It is written also here. But अब अगर आप इसको compare करें with a very fast compression, if it is very fast compression, तब क्या होगा? Then what will happen? The molecules which are near the face of this piston will not have enough time to escape, and they will have a pile up in a smaller region. So ये जो pressure और volume का जो change है, this will not be evenly distributed. Pressure near the piston will be high, pressure away from the piston will be very low. So you cannot trace these intermediate paths accurately because pressure is not distributed evenly in the whole gas. So you cannot trace the path between 1 and 2. It means you will know only the initial state, initial pressure and volume, and final pressure and volume. And because this process was very fast and it was not possible for us to trace its path accurately on this diagram. So then between 1 and 2, when we do not know the exact path, then we show it with dotted line. Then we do not know what is the exact path, and then we cannot find out from this diagram or theoretically the area under the curve because the curve is not known. Only the initial and final states are known. So such process is known as non-quasi equilibrium because it is not following, it is not passing through infinitesimally close to an equilibrium state. ये equilibrium states को follow नहीं कर रहा, ये कोई disequilibrium states को follow कर रहा है between 1 and 2. That's why we cannot trace its path. We cannot find its PV product theoretically. So that is called non-quasi equilibrium. So in such cases, we have to be relying on experimental methods to find out the work done. Because यहाँ पर हम work done हम find करेंगे because it's a very fast compression. We cannot calculate this, but we cannot trace its path, so we cannot find out its work done theoretically or mathematically using this diagram or area under this curve. So then we have to rely on experimental methods. And most of the devices and most of the processes are actually non-quasi equilibrium or non-quasi static in nature. So in such cases, we have to rely on experiments. So there are a large number of experimental data available, and that we can use. With the help of that experimental data, we can at least tell that theoretically it would have followed such path. इसलिए हमारे पास जो एक्सपेरिमेंटल से जो वर्क डन आ रहा है वो तकरीबन इस पाथ के इक्विवेलेंट है. So then we do thermodynamic analysis like this one. So ये मैंने explain कर दिया आपको. Processes in non-quasi equilibrium due to pressure. In this case, it is non-quasi equilibrium because pressure distribution between initial state and final state was not uniform. Right. So in thermodynamics, we show the quasi-static process by solid line, which you can see here. Okay. Which means process path is continuous from some initial state to some final state, and it is passing through a number of successive equilibrium states. That is called quasi-static. Non-quasi-static process is denoted by dashed lines in thermodynamics because we do not know the exact path. We know only the initial state and final state, but the path is not known to us. Quasi-equilibrium process is actually an idealized process. We just assume that your process would have followed such path, and it is not a true representation of an actual process. Actual processes are non-quasi in nature, but there are ways to assume these non-quasi processes to as quasi-static processes, which we will learn in coming chapters. But for the time being, we need to know what is meant by quasi-static or non-quasi-static processes. Okay. So many actual processes closely approximate this quasi-process, and they can be modeled as quasi-equilibrium processes with negligible error. How we do it, we shall learn in coming chapters. कि हम actual process which is non-quasi और उसको हम quasi-equilibrium में कैसे assume करते हैं या transform करते हैं so that our mathematical analysis becomes easier or our theoretical work becomes easier. जी कोई question है? Okay, if no, then I go forward. So just मुझे एक दफा confirm कर दें, all of you are with me.
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes,
Yes, sir.
sir.
Yes, sir. Sir,
Okay.
go
Yes, sir.
Yes, sir.
Okay. It's fine. Okay, Ji.
Yes,
Yes,
sir.
So,
sir.
Yes, sir.
process diagrams. Right. ठीक है. So process diagrams plotted by employing thermodynamics. So ये हम thermodynamics में now we know what is meant by state. ठीक है, initial state or final state. Uh, Whenever there is a change of state, it means there is some process. ये process कोई heating process भी हो सकता है, cooling process भी हो सकता है. वही चार processes हैं जो thermodynamic systems में हो रहे हैं. Either it is heating, cooling, compression, or expansion. So during all these processes, what happens? Properties changes, and we show these changes of properties with the help of any property diagram, like pressure volume. In case of this compression expansion, we use pressure volume diagram. In case of heating and cooling, we have some other diagrams which we will see. Okay, so process diagrams plotted by employing thermodynamic properties as coordinates. ये देखना, thermodynamic properties are as coordinates P versus V. Okay, so with the help of these process diagrams, we can visualize the process very easily. Okay, so this is called in thermodynamics or in overall in engineering, we always use diagrams to fully understand something. Only theory is not enough. Theory is not enough. We need to visualize any process with the help of a diagram. Which type of diagram? This diagram is known as schematic or pictorial diagram. ये जो आपको show हो रही है. And this diagram is known as thermodynamic property diagram on some graph. और उस graph के ऊपर x और y axis पे कोई ना कोई thermodynamic properties show हो रही हैं. Because during any process, these thermodynamic properties are changing. So in thermodynamics or in other subjects of engineering, we always interested to show the system with the help of some diagram. This is called schematic diagram, and this is called thermodynamic property diagram. So with the help of these diagrams, we can visualize the process very easily. Right? So some common...
Excuse me, sir.
जी.
सर हम इसको डायग्राम से ही रिप्रेजेंट करेंगे या ग्राफ से भी रिप्रेजेंट किया जा सकता है?
ये ग्राफ ही है बेसिकली. इस वक्त हमने ये ग्राफ ही है, प्रेशर वर्सेस वॉल्यूम ग्राफ ही है, जिसको मैं
इससे नीचे डायग्राम है.
ये वाला
जी सर.
ये ग्राफ नहीं है. दैट इज कॉल्ड schematic डायग्राम. स्कीम से निकला हुआ schematic. दिस इज द ग्राफ व्हिच इज आल्सो कॉल्ड प्रॉपर्टी डायग्राम. ठीक है.
इन
So ये
दोनों में से
basically
किसी एक के थ्रू हम इसको डिफाइन कर सकते हैं.
दोनों we shall be seeing जी दोनों के साथ. अभी हम जब thermodynamic devices applications हम study करेंगे, you will see both of these diagrams. Yeah, in some cases only this diagram is enough. In some cases only this diagram is enough. But to get a complete idea, we have to define both diagrams. तो ये मैं आपको explain करूँगा. अभी हमने जिस तरह boiler और condenser वाली जो example देखी है, उसमें हम अभी सिर्फ schematic diagram show कर रहे हैं, क्योंकि उसमें अभी हम कोई calculation नहीं कर रहे. जब हम calculations करेंगे, then we need to show that processes with the help of the graph also. ठीक है.
ओके सर, थैंक यू.
ओके. सो और इन डायग्राम्स में ये जो प्रॉपर्टी डायग्राम्स हैं या जो ग्राफ्स हैं, इसमें कोई ना कोई थर्मोडायनामिक प्रॉपर्टी शो हो रही है. एंड ड्यूरिंग एनी प्रोसेस, इफ एनी वन ऑफ द प्रॉपर्टी डज नॉट चेंज, then we use the term iso with it. For example, if there is some process in which pressure is not changing, then it is known as isobaric process. ये जो शो किया हुआ है, इसमें pressure भी change हो रहा है, volume भी change हो रहा है. Maybe during this process, if temperature is, यहाँ तो temperature axis नहीं है, but maybe there is a possibility कि ये कोई ऐसा process है जिसमें temperature change नहीं हो रहा, right? So when you compress a liquid, जब आप गैस को कंप्रेस करते हैं तो उसका टेम्परेचर भी राइज होता है. बट व्हेन यू ट्राई टू कंप्रेस अ लिक्विड, इट्स टेम्परेचर डज नॉट चेंज. ठीक है. So during any process, if any of the thermodynamic property is not changing or it remains constant during this process, then we use this prefix iso with it. ठीक है. If pressure during any process does not change, or if temperature during any process does not change, then it is called isothermal process. Other thermodynamic properties are changing, but any one of the thermodynamic property is not changing, then we use the prefix iso with it. So it could be an isothermal process if there is some process which is, जो हमने boiling का process हमने देखा था, उस boiling के process में temperature change हो रहा था. So that is not an isothermal process, but that was an isobaric process. In the boiling, during boiling process or during any heat transfer process, pressure does not change, only temperature change. So you may say it is an isobaric process because pressure is constant. If during any process volume remains constant, a process during which the specific volume remains constant, और ये होता है इन केस ऑफ लिक्विड, जब आप लिक्विड को कंप्रेस करते हैं तो उसका वॉल्यूम चेंज नहीं होता, सिर्फ प्रेशर चेंज होता है. इफ यू आर कंप्रेसिंग अ लिक्विड यू विल नॉट शो इट लाइक दिस कि वॉल्यूम, उसमें वॉल्यूम कांस्टेंट रहेगा, सिर्फ प्रेशर राइज होगा. सो यू विल शो इट with a straight vertical line because volume change in case of liquid compression is negligible. ठीक है, लिक्विड कंप्रेस नहीं होता, उसका प्रेशर राइज होता है तो वो फ्लो करता है. ठीक है, so then in that case you may say it is an isochoric or isometric process because volume remains constant, other properties may be changing. Now there is a term which is called cycle. So for हमने ये सिर्फ processes पढ़े. ठीक है, if for example there is another process, इसे मैं show करता हूँ. This is process 1 to 2, and if there is another process 2 to 1, there is a return process 2 to 1 by following some different path. ठीक है, so then now it becomes a cycle, right? Because you started your journey from point 1, you reach to point 2, then point 2 to again we are at point 1. So this completes a cycle. So to complete a cycle we need at least 2 processes. There could be more than 2 processes, but at least we need 2 processes to complete a cycle. अब वही जो हमारी एग्जांपल है, बॉयलर, टरबाइन, कंडेंसर और पंप, राइट? इसमें क्या हो रहा है, योर फ्लूइड starts from here. For example, this is initial point, state 1, this is state 2, this is one process, 1 to 2. 2 to 3, there is turbine work, this is another process. 2 to 3, these are processes, not cycle. Then 3 to 4, this is in the condenser, this is another process, 3 to 4. Then 4 to 1, inside a pump, this is another process. So 1 to 2, 2 to 3, 3 to 4, 4 to 1, these are 4 different processes. But the combination of all these 4 processes is a cycle, because you started from point 1 and after a number of processes you end up at point 1. So now it becomes a cycle. So it is a thermodynamic cycle consisting of 4 processes, 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So this 1, 2, 3, 4 processes are making up a cycle. So cycle is clear because your system returns to its initial state. Right. So here, for example, if it is a isochoric process, on pressure versus volume diagram. So this is isochoric process. It means volume remains constant, but pressure may be changing. Here, pressure is constant, but volume is changing. Right. For example, when you are heating something, so उसका pressure constant रहता है, but volume, because उसका temperature rise हो रहा है और volume increase हो रहा है. So then it is called an isobaric process because pressure is constant, but volume is changing. Similarly, we shall learn these thermodynamic properties in coming chapters. One is called enthalpy. So this is temperature versus enthalpy diagram or temperature versus entropy diagram. So these are also thermodynamic properties which we will learn later on in coming chapters. So if during any process enthalpy remains constant, right, then it is called isenthalpic process. अगर x-axis पे enthalpy है. If on x-axis we have a property which is called entropy, and entropy remains constant and temperature is changing, then it is called isentropic process. So we will learn about these properties later on. So if during any process temperature remains constant, so it is represented by a horizontal line, and during this process temperature remains constant, so it is isothermal. And here it is an example of a cycle, right? From state 1 to state 2, then from state 1 to back to 2, it becomes a cycle. Okay. Next is another term which is called स्टेडी फ्लो प्रोसेसेस। जी कोई क्वेश्चन?
सर एक क्वेश्चन, सर ये जो साइकिल है इसके लिए पाथ डिफरेंट होना लाजमी है 1 से 2 और 2 से 1 तक, अगर सेम पाथ फॉलो किया जाए तो?
हाँ सेम पाथ फॉलो हो भी सकता है, लेकिन उसका जब हम अभी प्रैक्टिकल सिस्टम पढ़ेंगे यू विल नो कि अगर सेम पाथ फॉलो कर रहे हैं तो उसका कोई फायदा नहीं है। फॉर एग्जांपल
ओके
सीन मैं आपको बताता हूँ। फॉर एग्जांपल ऐसे शो यहाँ पे वही प्रेशर वर्सेस वॉल्यूम डायग्राम। ये आपने ये आपको वर्क मिला, ये कोई हाई प्रेशर पे था फ्लूइड 0.1।
जी
अब इसका प्रेशर ड्रॉप कर गया, जब प्रेशर ड्रॉप किया वॉल्यूम इंक्रीज किया एंड वी गेट सम वर्क आउटपुट। ये फॉर एग्जांपल टरबाइन हो रहा है, टरबाइन में यही हो रहा है ना, प्रेशर ड्रॉप करता
जी
है
सर
वॉल्यूम इंक्रीज करता है एंड वी गेट वर्क आउटपुट। अब अगर यही प्रोसेस हम 2 से 1 फॉलो करवाएं तो हमें क्या करना पड़ेगा? अब आपने इसको कंप्रेस करना है ना, अगर
जी
2
सर
से दोबारा 1 पे जाना है वी हैव टू
पंप
सप्लाई पंप, ठीक है। तो
जी
जितना आपको वर्क मिला 1 to 2, और अगर ये बैक जो प्रोसेस है, जो रिटर्न प्रोसेस है, वो भी यही
जी
पाथ फॉलो करे 2 to 1, तो जितना वर्क आपको
जी
मिला था उतना ही वर्क आपने इसको दिया टू चेंज इट बैक फ्रॉम
ठीक है
2 to 1। So it means there is no net work output. So ideally what we
तो
want, जितना
सर
हमें
एनर्जी
वर्क।
भी तो यही कहती है ना कि एनर्जी सॉरी सिर्फ वो अपनी पोजीशन चेंज करती है, लेकिन वो जो है क्या कहते हैं डिस्ट्रॉय या क्रिएट नहीं हो सकती, तो
एग्जैक्टली
जाहिर बात है जितने
नहीं मैं आपको बताता हूँ, इसीलिए हम डिफरेंट पाथ फॉलो करते हैं। एनर्जी सेम रहती है, देखिए 1 से 2 पे आया, फिर हम 2
जी
से कोई 3 प्रोसेस पे जाते हैं और उस पे क्या करते हैं, वो एनर्जी हम क्यूसी कंडेंसर में,
जी
तो कंडेंसर में प्रेशर कांस्टेंट रहता है। अब हम यहाँ पे पंप यूज करते हैं, नाउ पंप इज फॉलोइंग अ डिफरेंट पाथ। तो एनर्जी कहीं नहीं गई, एनर्जी को हमें वेस्ट करना पड़ा टू फॉलो अ
ओके
डिफरेंट पाथ। ठीक है, ये सब कॉन्सेप्ट्स कमिंग चैप्टर्स में क्लियर होते जाएंगे। ठीक है,
ओके सर थैंक यू।
फिलहाल सिर्फ ये कि आपको डेफिनेशंस क्लियर हो, पूरे का पूरा प्रोसेस अभी क्लियर नहीं होगा, पूरे का पूरा सिस्टम अभी क्लियर नहीं होगा, बिकॉज दिस इज चैप्टर 1। ठीक है, तो
ओके सर
इसलिए
थैंक
वो
यू।
आपकी बात ठीक है कि इन सम केसेस ये हो सकता है कि आपका रिटर्न और जो पाथ है, इनिशियल पाथ है, वो सेम हो, लेकिन एक्चुअली मे बी थर्मोडायनेमिकली उसका कोई एडवांटेज नहीं है। तो वी वांट अ डिफरेंट पाथ, तो हम क्रिएट करते हैं एक डिफरेंट पाथ किसी तरीके से, लेकिन बाय
ओके
नॉट
सर
वायलेटिंग द फर्स्ट लॉ ऑफ थर्मोडायनेमिक्स। ओके जी, ओके जी। नेक्स्ट इज स्टेडी फ्लो प्रोसेसेस। अभी